Okay, I think it's time to start. Welcome everybody to the second web seminar in 2017. It's my pleasure to introduce you to Kamal Pangeni. He's a grad student at the Washington University in St. Louis. And today he'll talk about gap bridging enhancement of modified Urca processes in nuclear matter. So whenever you're ready, please start.
Okay, thank you.
Let me remind everybody to mute the microphones while he's talking.
Okay, can you guys see the screen and my pointer, I guess? Okay, good. So I'd like to thank the organizers for giving me this opportunity to talk about my research. So today I'll be talking about the gap bridging in nuclear matter. And this is the work done in collaboration with Professor Mark Alford. So in superfluid nuclear matter, transport properties are exponentially suppressed by as exponential of the gap over the temperature. Now, one way to overcome this, reduce the suppression, will be to reduce the temperature, to increase the temperature. But the question we want to ask is there another mechanism that can overcome this exponential suppression of transport properties in nuclear matter? And in this talk, I'm going to show you that the density oscillations of high enough amplitude can, in fact, unsuppress the exponential suppression by the mechanism of gap bridging. I'm going to tell you more about this idea of gap bridging. And this gap bridging works in the presence of density oscillations, and we know a lot of sources of high amplitude oscillations in neutron stars, such as star quakes and tidal forces in binary mergers. And there are also these armored unstable oscillations of rotating compact stars. Now, in presence of these oscillations that unsuppress the neutrino emissivity, we can get an enhanced cooling of the neutron star, because neutron star mainly cools due to neutrino emission. And if you have an enhancement in neutrino emission, we get enhanced cooling. This also helps in damping of the armored oscillations. Now, the topic of superfluidity and superconductivity in neutron star is now considered to be well established. So we know in the inner crust of the neutron star, we can expect the superfluid of free neutrons and the lattice of heavy nuclei. And in the outer core, we have a superfluid neutrons and superconducting protons. Now, to give you some numbers, at the core of neutron star, the gap is typically in the MeV range, and the temperature is around 0.01 MeV in that range. So the suppression is as large as 10 to the minus 40. Okay. So in presence of the superfluid matter, all these transport properties are very suppressed. The suppression is relevant in both hadronic matter and even in the exotic form of matter, such as the quark matter, if they are present in the inner core of the neutron star. Now, the presence of this Cooper pairing gap suppresses the beta equilibrium rate, and then it suppresses the neutrino emissivity. That's because the neutron decay is either Pauli blocked or energetically unfavorable. If you look at this figure on the left-hand side, where I have shown the neutron energy spectrum and proton energy spectrum with a gap, because of the gap, the neutron in the top of its Fermi sea cannot decay into a proton, because it can try to go it can decay into a proton below the Fermi energy, but that is Pauli blocked, because all these states are fully occupied. And the neutron can try to decay into a proton above the Fermi energy, but that state, you have the energy barrier because it's above the Fermi energy, and you have to cross this energy barrier. Because of these two cases, this process of neutron decay in superfluid nuclear matter is suppressed, so you cannot emit a neutrino. That's where the suppression in emissivity comes from. And because neutron star cools mainly due to a neutrino emission, this suppression in neutrino emissivity will slow down the cooling of the neutron star. Now, next I'm going to talk about the role of density oscillations. First, we'll look the role of density oscillations in normal matter where you don't have any Cooper pairing. So density compression actually changes the Fermi momenta. So if we have a relatively fast compression of, then the neutron Fermi energy is raised relative to the proton Fermi energy. So on the left hand side, I have shown you the energy spectrum of at beta equilibrium. So you have a neutron spectrum and the proton and electron spectrum. If we have a compression, density compression, the neutron Fermi energy is raised relative to the proton one. So you are out of beta equilibrium. And now the neutron can decay into a proton and then achieve a new equilibrium. In this process, you emit more neutrinos and hence enhance the neutrino emissivity. And this has been known for some time that if you are out of beta equilibrium, you enhance the reaction rate and neutrino emissivity. Now we want to see what happens when you compress, when you have a superfluid nuclear matter. So in the superfluid nuclear matter, you have this gap in the energy spectrum. So if you have a slight compression, the neutron Fermi energy is raised relative to the proton one, but you are not gaining much because if the neutron wants to decay into a proton over here below the Fermi energy, it is still Pauli blocked. To go to a proton state above the Fermi energy, you still have some energy barrier you have to cross. So having a slight compression in case of superfluid nuclear matter does not help you much. But if you have a large enough compression where the neutron Fermi energy is raised, now in this case, the neutron can decay into a proton above the Fermi energy. So you have all these empty states. And now suddenly you open up this phase space that enhances the neutrino emissivity a lot. So this is the basic idea of gap bridging. If you have a high enough compression, you open up this phase space and then the neutrino emissivity is enhanced a lot. And this is relevant whenever you have a reaction that changes flavor, like a neutron going to a proton or up quark going down going to a up quark, and in the process emitting a neutrino. Now, you can apply this idea and calculate you can see that phenomena by calculating the emissivity. So here in this plot, I am showing you the x-axis is mu delta. That's how far you are from the beta equilibrium. So as you go to the right, the density of oscillation, the amplitude of oscillation is larger. And the y-axis, it's the modification function. This is just the ratio of emissivities. So you are taking the emissivity at finite compression and with some gap and dividing by the emissivity at zero compression and zero gap. So this quantity is normalized so that if you don't have any gap and any compression, it is 1. So if you look at the top black curve, so this is for a normal matter. So it starts at 1. So when you don't have any compression, the emissivity is 1. And even in the normal matter, if you have a compression, it increases and the increase is polynomial. Now, if you have a gap, if you have nuclear matter with gap, then thing is even at zero compression, the emissivity is highly suppressed. So we can look at any one of these plots. So let's focus on delta over T of 25. So you can see because of the gap, the emissivity is suppressed. The suppression is around 10 to the minus 7 here. And if you have a higher gap of 50, the suppression is even larger. Now, as you go to the right, you are increasing the amplitude of oscillations. As we talked previously, the initial slight compression does not help much. So if you are compressing it slightly, the emissivity is not increasing. It remains a constant until you reach a critical value, at which point the emissivity starts to increase. And keep in mind, this is a log-log plot, so all these straight lines are actually the exponential increase. So once you reach some critical value, the emissivity increases, and it even reaches the ungapped. So the black line is for the ungapped nuclear matter. So at very high compression, you are reaching the ungapped limit. And this was done in 2012 by Mark Alford, Sanjay, Reddy, and Kai. And this was done for 1s0 neutron pairing and direct Urca process. But the drawbacks of this calculation is if you want to apply this to a neutron star, in neutron stars, this direct Urca process is forbidden because of energy momentum conservation. And to have a direct Urca process, the proton concentration needs to exceed some critical value, like it needs to be around 10–11%, which we don't have in most part of the neutron star. So it's not the direct Urca process that happens in the neutron star. And in the inner regions, the neutrons don't pair in 1s0 channel. It's repulsive in 1s0, but attractive in the 3p2 channel. So in this work, what we did was we looked at the gap bridging in case of modified Urca process with 3p2 neutron pairing. But we did our research in 2 steps. First, we looked at modified Urca with 1s0 pairing, and then did the 3p2 pairing. So I'll show you the results for modified Urca with 1s0 neutron pairing and the 3p2 neutron pairing. In all these cases, the protons are always in 1s0 channel because the density of proton is so low that we expect the proton pairing to be in 1s0 channel throughout. So modified Urca process, so here is the Feynman diagram for modified Urca process. So in modified Urca process, you have a spectator neutron. So N1 and N2, 2 neutron, that one of them decays into a proton and in the process emit a neutron, and you have the other neutron that's a spectator that's sitting there. It is necessary to conserve momentum and energy. So that's the sole purpose of this spectator neutron, but it complicates the calculation a lot. So in modified Urca process is slightly different from direct Urca, where you have a spectator neutron sitting there to conserve energy and momentum. Now, the question we want to address is what role does this spectator neutron has? So this neutron is just sitting there, it's not changing its flavor or anything. So does it have any effect in this gap bridging? That's one interesting question we'd like to address. So in the plot, we'll be calculating the emissivity because we have so many 2 initial neutrons and 1 proton, neutron, and electron in the final state. The calculation of emissivity is highly complex. So we have to integrate over the phase space of the neutron energy. And in the plot, I'll be showing you this modification function. As I told earlier, it's the ratio of emissivity divided by the emissivity at 0 gap and 0 compression oscillation. So this depends on this compression of oscillation and the gap. The gap is trying to decrease the emissivity. It suppresses the emissivity, where this mu delta tries to enhance the emissivity. So we have battle between one quantity that tries to enhance and the other one that suppresses the emissivity. So here is the result for the 1s0 neutron and proton. So both the neutrons and protons are in 1s0 channel. And we are plotting as a function of the compression. So that's how far off you are from beta equilibrium. So as you go to the right, you are going at high amplitude of oscillations. And we plot it for various different temperatures. So if you look at zero compression, these are highly suppressed. The delta n over t equals 80 has suppression as large as 10 to the minus 80. So lower the temperature, the higher the suppression you have. And as you increase the density of oscillations, initially you have a not much increase in the emissivity, and at some critical value, it starts to increase exponentially. So this is a log linear plot. So all these straight lines are exponential increase. And they increase, and when this mu delta over delta n is around 4, you reach order 1. That's when we say it's a point of complete gap bridging, where all the exponential suppression is overcome by these density oscillations. So no matter how low the temperature is, by the time you are at when your mu delta over delta n is 4, you completely overcome the suppression from the superfluid gap. So initially your suppression is roughly exponential of -2 delta over t, and by the time your mu delta is 4 times delta n, the suppression is completely overcome. Now, if you look at the plot, this has a typical staircase kind of structure, and to understand this structure, what we can do is we can look at the different subchannels that contribute to the modified Urca process. So here I'm showing you the modification function, but for different channels within the modified Urca process. So I'm taking one of these curve, the delta n over t of 60, and looking at the subchannels to better understand where that step structure comes from. And you can see there are 16 channels, but they nicely fall into these 5 different classes. And for some channels, if you increase the density of oscillations, it does not do anything, but there are these other channels that open up and then they saturate. So the addition of all these subchannels will give you, so basically the envelope is giving you this step structure. Now, let me show you what I mean by these channels. So this is one particular channel. So here you are looking at, so the left-hand side is the neutron spectrum, proton, and the electron spectrum. So in this channel, you are taking a neutron, the spectator neutron starts at above the Fermi energy, where the neutron occupation is sparse. So you are starting from a place where there are not many neutrons, and it's going to a state where you have almost fully filled neutrons. Now, and then you have the other neutron that decays into a proton, the protagonist one, that starts below the Fermi energy, where you have a lot of neutrons, and goes to a state in the unoccupied proton state. Now, this process has a suppression roughly of exponential -2 delta over t. That basically comes from this part over here, where you have a spectator neutron, because in this channel we are taking the neutron that starts at sparsely populated region. So it's very hard to find a neutron over here. So that gives you basically a suppression of e to the minus delta. And then that neutron goes to a state where you have high density of neutrons. So it's very hard to find the unoccupied state. So you have a further suppression of e to the minus delta. So that basically gives you e to the -2 delta suppression. Now, if you increase the density of oscillations, it is true that the neutron Fermi energy is raised relative to the proton one, but that does not enhance the it will not enhance the suppression factor, because if you look at this spectator neutron, this is still starting at the sparsely populated region where you don't have that many neutrons and going to a other region. So you still have this exponential suppression. So just having this density oscillation does not help in this kind of channels. So those will be something like this channel number 4 and 5, where even though you have density oscillations, you don't gain much. But if you look at other channels, like where you take both neutrons to be in this region where you have high occupation of neutrons, and then the spectator one jumps above the Fermi energy, and the other, the protagonist one, goes to a proton in the unoccupied state. Now, this has initial suppression of e to the minus 4 delta. That's coming from this energy barrier, because you are taking both the neutrons up in energy, and that needs energy. So that is basically giving you a suppression of e to the minus 4 delta. The other way to think is, because you are taking both neutrons up in energy, the electron has to go down in its Fermi energy, where all the states are occupied. So this gives you a suppression of minus 4 delta. But now if you increase the density of oscillations, now this channel, for this neutron turning into a proton, you don't need any energy. And then you just have this energy suppression coming from this neutron going up in energy, which forces the electron go down in its Fermi energy. So you still have a suppression of e to the minus 2 delta over t. So here the compression does affect. So you start at e to the minus high suppression, and then you end up e to the minus 2 delta. If you even increase the suppression, you can overcome all this suppression coming. So basically, so the last one I told you will be the channel 1, where you start very low. The suppression initially is e to the minus 4 delta, and that channel increases and basically reaches of order 1. So the sum of all these subchannels give you the step structure. Okay. So that basically explains where the step structure is coming from in our plots. Next, we looked at the 3p2 neutron pairing. So the previous one was for 1s0. So for 3p2 neutron pairing, there are still, you have certain choice for the orientation of the condensate. Like the JINA-CEE can be 0 plus or minus 1 or plus or minus 2. There has been microscopic calculation to see which one is the favorable one. And it turns out from the microscopic calculation that the 0 subchannel, JINA-CEE equals 0, is slightly favorable to the other ones. But there is this uncertainties in microscopic calculation. So instead of just looking at this 0 subchannel, we looked at the JINA-CEE equals 0 and JINA-CEE equals plus or minus 2. The reason for choosing the second one is because we expect them to show some qualitatively different emissivities, the qualitatively different features, because this JINA-CEE equals 0 in this channel, the Fermi surface are all gapped, while in the JINA-CEE equals 2 subchannel, you have some node in the Fermi surface. So we want to see what the role of those nodes will be. So first, we look at the JINA-CEE equals 0. So the channel where the JINA-CEE equals 0. And here the angular dependence of the gap is given by this function where you have square root of 1 plus 3 cosine square theta. The thing to notice is this does not vanish anywhere. So it has a minimum of 2 delta at the equator, and at the poles it has a maximum of 4 delta naught. since we have a minimum of, since this gap is minimum at the equator, all the three neutrons tries to align itself in the equator, so they spend most of the time. So the major contribution to the integral is just coming from near the equator region where the gap is effectively delta. So this case, even though it's a 3p2 neutron pairing state, and because all the neutrons mostly live in the equatorial region where the gap is effectively delta, we expect the result to be similar to that of 1s0 pairing. So if you look at the results, the plots from numerical integration, and it again shows the same step structure, and it's slightly different in terms of magnitude. This is about a factor of 40 less than the 1s0 channel, but given the magnitude of the range, because we are going from 10 to the minus 70 to 10 to the 12 or something, this, even if we plot them on the same plot, it's hard to see this factor of 40. So they will basically be almost on top of each other. But that's what we expect because of what I said previously. Next, we go to the modified Urca process with the 3p2 but JZ equals 2 neutron pairing. So here the angular dependency has a sine theta, so it has a pole. So that's the Fermi surface. So we have a pole on the equator, we have a node on the poles. Now, even though we have these nodes in the poles, not all three neutrons can benefit from it because we still have to maintain the momentum conservation. So these two neutrons must add up to the third neutron and the momentum of the proton and electron, which I ignored in this picture because in the modified Urca process, the proton and electron moment are relatively small compared to the neutron ones. So we just look at the three neutrons. So the momentum conservation tells us if you have one of the neutron along the poles, you cannot have the other two. So these two will essentially be gap, but the gap is not delta, but little bit smaller. But still, even though you have a pole, you cannot get rid of all the separations. So here is the plot of modification function as a function of this mu delta. So we still have high energy, high separation. Okay, let me compare with the other one. So you still have a exponential separation at zero compression oscillations. And then as you increase the compression, then it reaches the uncapped limit, which is of order 1 over here. So if you compare the zero subchannel and JZ equals 2, you can clearly see this one is even initially suppressed smaller. It has a smaller separation. That's because that's expected because we have this node in the poles. So as you can see for delta and not over T80, so this is a 10 to the minus 17. This is somewhere around 10 to the minus 50. We start at low separation, and where for the JZ equals 0, the complete gap bridging is around 8 mu delta. This ratio is 4, but for the other one, it's around 2.73. So this one reaches the uncapped value faster, and it's basically because you have this node in the Fermi surface that helps you. So if we compare these two subchannels, as expected, the lower separation is in the JZ equals subchannel. And for this one, the complete gap bridging is around 2.73. So, but the overall point is, no matter which subchannel you are at, you start with a high suppression due to the gap, and because of the density oscillations, it overcome the exponential suppression. And the point where this complete gap bridging happens depends on which subchannel you are looking at. And in this case, if this channel, the two subchannel is favorable, then you get the complete gap bridging much earlier. You don't need that much of a high amplitude of oscillations. If this is the favorable channel, then you need little bit more higher amplitude of compression. So, okay, so let me summarize. So we have shown that the exponential suppression of flavor changing beta process in superfluid nuclear matter can be completely overcome by the mechanism I described before called gap bridging. And this is basically due to the compression oscillation of sufficiently high amplitude, and it is true regardless of how low the temperature may be. So in this case, in all the cases, we have different temperatures, but by the time your mu delta over delta n is 4, you overcome the exponential suppression. So because the enhancement of transport properties such as neutrino emissivity that determines the cooling of the neutron star, and this density oscillation increases the neutrino emissivity, this will definitely lead in the enhancement of the cooling, neutron star cooling. And there has been recent suggestions by Gusakov where you get the additional enhancement in this exponential suppression from the high velocity flow of the superfluid related to the normal fluid. Here the suppression is coming because of this relative flow of the superfluid, it will suppress the gap itself. So the gap itself is decreasing. That's why the suppression is coming, which is slightly different from, which is actually different from the gap bridging mechanism. But I just wanted to point out that there are other suggestions of how these exponential suppressions can be overcome. Now, in future, what we want to do is we want to include the density dependence of the gap bridging. So in this calculation, we just chose a value of the gap at particular density. We did not worry about the density dependence. If you look at the gap as a function of density, it is like a bell shape. So it does depend on the density. We ignored that fact, just looked at some particular density and did the calculation. But in future, it will be interesting to look at the density dependence of the bearing gap, and then effect this mechanism of gap bridging in the calculation of cooling models of neutron star. All right, thank you.
Thank you very much, Kamal, for this very interesting talk. As usual, for questions, please indicate in the chat if you want to ask one.
We have questions at MSU.
Sure, go ahead.
Yeah, what would change if you were included magnetic field in the calculation?
So that's a very good question, and we have not thought about the we have not given much thought about including the magnetic field, but yeah, it's a good question. I don't have a concrete answer right now. Sorry about that. Yeah, but that's a good possibility to look at how the magnetic field will affect all these scenarios, because we know in the neutron star we can have magnetic fields, very high. Yeah, but I didn't have any ideas at the moment. That's a
More questions?
Yes.
Jerome here has a question.
okay.
Is it possible to convert this ratio delta over 2 in terms of percentage of density oscillations?
Yeah, so you can do that for that. So this is a generic thing we did not. So if you want to convert, then it depends on the equation of state, what kind of matter you are looking at. But it's possible to convert. And in the first PRL paper, they have given a relation how you can convert this chemical potential into the percentage of density fluctuations. And normally the amount of fluctuations you need is like 10 to the minus 4 something. So if you have a fluctuation delta n over n of 10 to the minus 4, then that can overcome the suppression we are talking about.
So this estimation is for the 3p2 channel or for the 1s0 channel?
Okay, so that one was from 1s0 channel, but in 3p2 the magnitude of the gap is even smaller. So that will lower it down, but since you have a lot of more particles in this case, that might, so it should be around 10 to the minus 4, around, even for the 3p2 channel. But we have not done that conversion, but it should be around that number.
And you have an idea of which process can generate such large density oscillations?
Oh, so it will be the unstable R modes. They also have very large density oscillations. And then it can be the star quakes, but I don't know in case of star quakes how big the amplitude of oscillations is, but may reach that high of a magnitude. It's not 10 to the minus 4. It's not large, but
okay. Thank you very much.
mm-hmm.
More questions?
Yeah, I had a question. I'm Danny Page in Mexico.
Oh, okay.
If I understood correctly, you almost always assume that you have a gap for neutrons and protons that are the same size, roughly, no?
Uh-huh.
But what if the proton gap is much larger? Because usually the 1s0 of proton is much larger than the 3p.
Yeah. So that's true, because the proton has a 1s0 pairing, which is much larger than the 3p2 one. So if you read the paper, we did look at how changing the proton gap changes the whole picture. So in the plots I show you, we have the neutron gap and the proton gap to be the same. It just makes the calculation easy, but we did look at, it makes the analysis much easier, where you explain where all this step structure is coming from. But you can always put the proton gap, which is larger than the neutron gap. We did that calculation, and the effect, yeah, so it's expected. It does not have like unexpected behavior or something. But in the paper, we did show the plots where the proton gap is like much larger than the neutron gap.
Okay.
That's a good point, actually.
The paper is published or just in the archive?
Oh, it's published in PRC.
Okay.
It was recently published, like 10 days ago or something.
Okay. Okay, thank you.
More questions for Kamal? If there are no more questions, then let's thank the speaker again. And I hope to see you all in our next seminar meeting.